How's everybody doing? Professor Bryant back with another installment of Workout Wednesdays. This is going to be about kinetics, specifically about the Arrhenius equation and how to use it to determine different rate constants at different temperatures, or different temperatures associated with different rate constants. We should be familiar with the equation that is shown here on the right in the PowerPoint. This equation again will be given to you, all three of the equations you see here, and more specifically, this particular problem is going to work with two different temperatures or two different rate constants. So let's take a look at the worksheet. This worksheet has been uploaded to D2L. This is a worksheet that has a question involving a decomposition reaction, and that decomposition reaction involves nitrogen, oxygen, and chlorine decomposing into two gaseous products. So they have given us a K value, and they have given us a temperature that K value is at, and they've given us activation energy. So we have three of the variables we need, and then they give us the fourth that we need to solve for, and they ask us what is the rate constant at 130 degrees Celsius. So let's go ahead and answer that. Okay, so what we want to do with this value is take a look at what we have. I always like to write down the information that we have. Think about the units, make sure that we are converting if necessary. I like to go ahead and convert temperatures. We need to be working in Kelvin. So this is 403 Kelvin. 100 degrees Celsius is 373 Kelvin. So I like to go ahead and change that. One thing that you'll notice about our activation energy is that it is in kilojoules per mole, and the gas constant R, which is on your reference material, it's a constant, it's always the same, is generally given in joules, so we need to convert that to kilojoules, and I've done so by multiplying it by 10 times 10 to the negative 3. The K value that we were given in the problem is K here. One thing that you're going to have to be able to do is to manipulate and rearrange equations. So I'm not going to show the rearrangement of this equation, but I am going to be solving for K1, meaning I want the K that we're looking for to be K1. It's just going to make the math a little bit simpler. So if we make this K1, then this has to be T1, which means that over here, our starting information has to be K2, and therefore our starting temperature, or the temperature that we were given, not starting necessarily, temperature we were given. So if we rearrange this equation, we end up with K1 equal to K2 times exponent raised to the activation energy over R multiplied by 1 over T2 minus 1 over T1. And I'm going to put this up. Okay? And that's just following the equation, and remember that exponential is the inverse function of natural log, because natural log is a function. So if we plug all of these values in, right, we end up with 9.3 times 10 to the negative 5 molar seconds, exponent raised to the activation energy 99 kilojoules per mole, all over 8.31 times 10 to the negative 3 kilojoules per Kelvin mole, multiplied by 1 over 373 Kelvin minus 1 over 403 Kelvin. So hopefully we can see that. If you're not clear right now, I would suggest that you pause the video, go back, rearrange your equation so that you're solving for the variable of interest. In this case, I've used K1, and make sure that you can get to this point, because this is the important point. Everything after this is just computation and plugging it in the calculator. So therefore, once we plug this in the calculator, what you're going to see is that we're going to end up with 9.3 e to the negative 5 times exponent raised to the 99 over 8.31 e to the negative 3 multiplied by 1 over 373 minus 1 over 403, and the answer is 0.00100. Exponentials and natural logs are unitless after the function is carried through. Therefore, our units are a function of just what we have from K2, so we should have same K units. We have not changed the order of the reaction, so we should expect these units to be the same. Now, if we take a look at that, 1.00 times 10 to the negative 3, and we compare this value to the other K value, we see that our K here is larger, and we are at a warmer temperature, a hotter temperature, right? So, as you increase the temperature, what do we know from the basics of kinetics? We should expect that the initial rate should be faster, therefore it makes sense that the rate constant is in fact larger. Remember, the rate constant is involved in the mathematics of all of these different reactions. Okay, so let's take a look at part 2. And part 2 of the question asks us, at what Celsius temperature will the rate constant be 5.1 times 10 to the negative 7? So we are now being asked to do the opposite. Instead of looking at K at a different temperature, we want to look at T at a different K. So they want us to know what is T1, let's say, at a K equal to 5.1 times 10 to the negative 7 molar per second. Inverse molar. Okay, so now we must rearrange the equation to solve for T1. Okay, so if we look at the original equation, ln K1 over K2 is equal to EA over R, 1 over T2 minus 1 over T1. What we can see is that with the initial rearrangement, if we divide both sides by activation energy, we end up with ln of K1 over K2 divided by EA over R equals 1 over T2 minus 1 over T1. If we add 1 over T1 to both sides and then subtract this to the other side, we end up with 1 over T1 equals 1 over T2 minus ln K1 over K2 all over EA over R. Again, here's another scenario where right now, if you're not sure how that rearrangement went algebraically, work slow, be patient, but pause the video and make sure that you can get to this point where we are solving for T1. Remember, if we're solving for T1, then that means this must be K1, and in this particular case, that means we're still dealing with K2 and T2, which is the initial information that was given to us. So to plug all of that information in is going to involve 1 over 373 Kelvin minus natural log of each of these K's. So we have K1, 5.1 times 10 to the negative 7 molar seconds all over 9.3 times 10 to the negative 5 molar seconds all over 99 kilojoules per mole all over 8.31 kilojoules per mole Kelvin. That leaves us with 1 over T1 equal 2. And if we do the math here, on the calculator. Be sure to be very careful when you're putting this in. Notice I put parentheses around everything. Order of operations is very important. 1 divided by 373 minus natural log 5.1 e to the negative 7 divided by 9.3 e to the negative 5 divided by 99 divided by 8.31 e to the negative 3. We end up with 0.003117. Remember, these units are inverse Kelvin. Therefore, T1, when we do the inverse, we end up with 320.7 Kelvin. Now, notice we end up with a temperature that is less than this temperature, and it makes sense that we have a K, or a rate constant, that is less than the rate constant. The rate constant and temperature are generally directly directly proportional. As you increase one, you increase the other, and vice versa. So I hope this was helpful. If you have any questions, again, make sure you send me an email or leave a comment if necessary, and I can answer that for you. So again, this is Arrhenius equation, chapter 14 of the text. It's going to be over kinetics. All right. Thank you.